So, okay. Uh, yeah, I will. So this will be the last lecture of this introduction to quantum Hall effect. So let me just quickly recap about what I said in the previous lecture. So previous lecture, we started to try to understand the physical mechanism for the integer quantum Hall effect, right? We did two things. The first thing is that we consider an ideal situation that I only have electrons moving in the presence of magnetic field, no interactions, no disorder. So that the ideal situation, right? And there we learned that, so we spent almost 2 lectures talking about what's the solution of that case. And we know that, we learned that, so we basically have complete flat energy levels that is called lambda levels, right? And each lambda levels have a very extensive number of degeneracies, which is basically like how many flux quanta are there in the system, right? And what we learned is that in this ideal situation, if I occupy integer number of lambda levels, let's say we occupy those lambda levels, and then so let's say we occupy new lambda levels, and then what we can compute the resistivity conductivity of this state, and then we end up with that we have this Hall resistivity to be 2 pi h bar over E square times 1 of nu, right? And nu is really just the number of lambda levels that we occupy, right? And also we have computed that rho xx equal to 0, right? And alternatively, we can also we can also use conductivity rather than resistivity to describe the system, and the conductivity sigma xy will be just inverse of rho xy, and it will be E square over 2 pi h bar times nu, right? And the sigma xx is still 0, right? The reason is because here we have a matrix rather than a number to characterize the conductivity or resistivity, right? So this result is nice. It's actually telling us that the experimental observation of the quantum Hall effect is related to lambda levels, right? In particular, that we feel an integer number of lambda levels, right? But it doesn't really explain the experimental observation that we have plateaus, right? So again, let me draw this plot. So you ask, how is the resistivity, Hall resistivity change with the magnetic field? And classically, you would say it's just proportional to the magnetic field. But in the quantum world, what you end up with are those very robust quantized plateaus. And at each plateau, we have, let me use this color. So at each plateau, we have those Hall resistivity to be quantized at this value, right? And so now, if I'm staying in this ideal situation, let's say we occupy new number of new lambda levels, right? I get this precisely quantized Hall resistivity. But now, once I started to change the magnetic field, that is effectively like change the number of electrons, I will start to occupy a higher lambda levels, right? But I won't have enough number of electrons to completely occupy that lambda levels. That means I will get some, the Hall resistivity coming from that state will be non-quantized, right? I won't really say this type of plateau, right? Instead, I would probably still say the classical behavior that my resistivity, Hall resistivity keeps on changing with the magnetic field, right? And the solution to the presence of this very robust Hall resistivity plateaus comes from the dirtiness of the world, the reality that you can call the impurity, or sometimes generally we call such as disorder, right? And it's really this dirtiness of the real world give rise to this remarkably quantized Hall plateaus. And I have explained that, let's say if you have those impurities and disorders, what you will end up with is that those complete flat lambda levels, highly degenerate lambda levels, will get perturbed. And in particular, there's no reason you still have degeneracies. So that means, so those, I will just have non-degenerate state, right? Let me write it as here. So yeah, just I have each lambda level so becomes rather broad, will be broadened, and I will no longer have degeneracies. So I should not really draw another axis like the quantum numbers, momentums, and so on, right? And the most important effect of disorder is that among those states, most of them will just be localized by the disorder, right? I provide a picture that, let's say my disorder is just some pretty random configurations of potentials, right? And then those states, the states that here will be really just localized at the maximum and the minimums of just around the impurities, right? And intuitively, and you can show more rigorously that those states will not contribute to the conductivity. And among those states, we only get a very few states sitting in the middle of my spectrons. Those are what we call extended state. And those extended states will contribute to the conductivity and resistivity, right? Those states are what we call localized state. Let me capitalize this E. Called localized state. And those localized state will not have any, it will not contribute to any thing to the resistivity or conductivity, right? Then the picture becomes rather clear that now you consider a situation that I'm start to throw in electrons in the system. The electrons, due to Pauli exclusion principle, then the electrons will start to fill the system. I mean, it will fill the system starting from the low-lying energy state, right? It will just start from here, and it will so then before it hit the extended states, the resistivity and the conductivity, the Hall resistivity and the conductivity is really just zero, right? If I starting from the vacuum, right? And once I start to occupy those extended state, I will say that my resistivity, right, that should be something like this, and you will say the Hall resistivity will get some sudden change, right? The extended states are pretty rare compared to the extensive number of localized state. And once I occupy the entire extended state, I will again start to occupy those localized state. Then I get some finite number of resistivity, right, Hall resistivity, and the resistivity will stay unchanged as I started to fill those localized state, and I keep on doing so until I start to occupy the extended state at the higher lambda levels. That's get me another change of this Hall resistivity, right? It's like, yeah, so for when I started to fill this state, that's correspond to this region, right? Once I fill the extended state at the second lambda levels, then I will again stay in this plateau. So now I hope it becomes clear that why we get plateaus, why we can get plateaus in the Hall resistivity. It's really the consequence of disorder which makes most of the state localized. Those localized states do not contribute to the resistivity or conductivity, right? But now that comes another dilemma, right? So because for quantum Hall effect, for integer quantum Hall effect, it has two key features. One is that we do get plateaus for the Hall resistivity. The other feature is that the Hall resistivity is quantized, right? It's really just a combination of the two physical constant and times 1 over integer, right? So from this ideal situation, we know how this number comes from, right? It just comes from that the fact that when you entirely fill one lambda levels, one ideal lambda levels, you get this number, right? Now, you might be wondering, okay, in the reality, once we have those disorders and so on, right, this number may change, right? In particular, you learn that due to disorder, I get a lot of localized state. Those localized states do not contribute to the conductivity at all, right? So then how can those those very few extended states still give me the exact number of this Hall conductivity? That sounds a little bit crazy, right? So, and the answer to this question is that is a so-called topology. So let me write it there. So it is the topology actually really makes it that no matter what happens here, as long as you entirely fill one lambda levels, you will always get that quantized resistivity, right? So that's the answer. So and the plan of this lecture is really try to explain this fact, right? How this Hall resistivity is related to the topology and why it is quantized. Okay, yeah.
Excuse me, so if I'm getting this recap right, then we can kind of see these plateaus just as a direct consequence of the energy gaps between the extended states, right?
Energy gap between extended state, yeah. Yeah. So any other questions? Yeah.
Wouldn't the degeneracy of extended states change with B?
No, it doesn't. Yeah, it's a different from that, right? The number of extended states really depends on the configuration of your disorder or impurities, right? So are you asking like the contribution of the conductivity of those extended state? That's your question? You're not asking the number of extended state, right? You're asking the number of extended state will really depends on the configuration of your impurities and disorders. That is totally non-universal thing. But then the universal thing is that no matter how many extended states you have, if you compute the total conductivity or resistivity, Hall resistivity will always be this number. The total number will be this. And that is a consequence of topology. Any other question? Okay, so the punchline of this story is that the Hall conductivity is Chern number. So Chern number is a topological invariant. It's probably one of the simplest topological invariant in algebraic topology, which I will also explain. But the punchline is really that the whole conductivity, of course, you want to, I mean, besides this, this universal, I mean, this number of physical constants, right? It's a Chern number, right? And this Chern number is always a quantized integer. So that's why it's always quantized. So to relate the conductivity with the Chern number that I'm going to talk about, so you need to make use of the so-called Kubo formula. So, in this lecture, I don't think I really have time to explain what this Kubo formula is and how to make the use of the Kubo formula to compute the conductivity, right? It's pretty, yeah, if you're interested, you can check the lecture notes of David Tong. So he has a very nice derivation like what is the Kubo formula and how to use Kubo formula to really compute the conductivity, right? It's going to be very similar like what I did in the last lecture that I just considered the ideal Landau level situation that I apply an electric field and then compute the conductivity, right, or resistivity. That it's going to be something very similar, right? And the discussion of those involving Kubo formulas will be a little bit technical, and it may so I think it would be better for us to really just say the essence of this statement. This whole conductivity is the Chern number, and why Chern number is quantized. That is more important thing for this lecture. Okay, so so I'm going to directly give you the way to of how do I compute conductivity and how I relate it to the Chern numbers. So I'm going to consider a geometry that is a torus geometry. So that's really just a donut, right? And it's closely related to the geometries that we considered at the beginning when we solved the Landau levels, right? The rectangle geometry and the torus geometry is really just that you take the periodic boundary conditions for both x directions and y directions, right? It's really like you glue this boundary with this boundary, and you glue this this boundary with left boundary with right boundary, then you do get torus. Right? You can play it with a paper, then you will say it, right? So so we are going to so the reason that we are going to consider the torus is that now I can have the two I can have two uncontractable loop, right? So one is along these directions, right? You can just consider you have a loop here, then there's no way for you to contract it to nothing, right? And we do get another type of uncontractable loop, right, like this. Okay, so then what we are going to do is that we add an extra perturbation to the system. That is, we thread a magnetic flux in the system. So one is that I thread flux in the hole of my torus that I called phi x. And the other type of flux is that I show it in this circle that I called it phi y, right? Then the consequence of this flux is really that for this phi x, if I have electrons moving on the torus, and if it moves in this uncontractable loop, right, it will then say this flux as this AB phase, right? Similarly for this phi y, if I do this type of movement, then I will say this phi y as a magnetic flux, right? So formally, what you can do is that for this type of problem, then we just ask how the system respond under those two magnetic flux. Okay. And what I'm going to consider is that, let's say we have a wave function, right? And this wave function is really just the states corresponding to that complete field at lambda levels, right? In this ideal situation, this wave function is really just the determinants. Let's say we feel the lowest lambda level, right? Then this wave functions, let's say we have n particles, and we label the positions of those n particles. This n, capital N, is the number of degeneracies of my lambda levels, like complete occupy that lambda levels, then I get this capital N number of electrons, right? And then its wave functions will be just a so-called Slater determinant of, let me omit the label of the lambda levels. So I'm considered lowest lambda level, but the situation for second lambda level and the higher lambda levels will be very similar, right? So So the many-body wave functions of the state will really just be a determinant of all the wave functions that you have for each lambda orbitals, right? Remember, this phi is really just this solutions of harmonic oscillator with the k chosen to be the momentums that you can have in the system. So here I'm just label those momentums schematically with the number of particles that I have. And I should have is x2 and it till xn, right? So that's the wave function we can have. That's the wave function that describes the states that I completely feel the lowest lambda level, right? It's called the Slater determinant. Yeah.
In the last row, are they all k equal to n?
Yeah. Okay. Yeah. Good. So sorry for the typo. Yeah. It's always like from 1 to n, and then for the first row for the x, for the coordinates, we choose x1, x2, and so on. Right? Yeah. Thanks. So it's called a Slater. I think it's called a Slater determinant. That's for non-interacting particles, fermions. That's always so if you consider, let's say, n numbers of non-interacting fermions, then its wave function would always like this. This phi will be just a single particle wave functions, right? You can easily say that this wave function is antisymmetric if you exchange two particles, right? Yeah. Yeah. We do have normalization. Let me put, yeah, thanks. Okay, so, and we are going to just to consider this such object, right? It's going to be a, that's the number of particles you have. Yeah. So then what we are going to consider is this many-body wave function, right? In this case, it's again just correspond to that I completely occupy the lowest lambda, the lambda levels, right? But those states gets perturbed due to the impurity and disorder, right? But in the end, it will be something similar. So but it will become very messy, right? Now you get to the sense of this many-body wave function. Its precise form of that many-body wave function is really not important to our discussion. That's the beauty of topology. You don't need to care about those details. So let's say we have a wave function. Now I'm going to omit all those like coordinates, right? And just have a wave functions of a Hamiltonian, right? That wave function corresponds to that I have n particles in the system. Okay. And now, remember, in this setup, I introduced two extra perturbations to the system. One is that I add magnetic flux I add magnetic flux in two directions, right? Then for different choice of magnetic flux, I will end up with a slightly different Hamiltonian. Hence, I will have slightly different this capital psi, right? So let me write this wave function just as a wave function with two variables. One is phi x, one is phi y, right? And for phi x and phi y equal to 0, and in the Klein limit, this wave function is really just this guy, right? But now we just have some object, some very messy wave functions depends on those two parameters. Okay, and now the statement of this whole conductivity is Chern number, which you can derive using Cooper formula, is that in the end, the whole resistivity will just be this number, this quantity. Let me, how should I do it? So it will be IH bar times partial psi with respect to phi x and partial capital psi with respect to phi y and minus minus the term that I swap phi x with phi y. That is what you can derive using a Cooper formula. If you're interested in how to derive this, you can check Daviton's lecture notes. You can also probably find similar derivations from other lecture notes or some on the internet. Okay. So and now I'm also going to massage this a little bit. So we are going to introduce two variables. That is just theta that I'm going to play with as 2 pi phi I over phi 0. Did I use phi 0? Let me see. This phi 0 is a flux quantum that I introduced right before, right? Just remind you, this phi 0 is just the unit of the minimal, the unit of magnetic monopole, right? Just like E is the charge of the unit of the charge. Okay, introduce this theta I, and then what you will have is, so that then I want to rewrite this whole conductivity using theta instead of phi. And in particular, the theta will then just take periodic values between 0 and 2 pi, right? And you can say that this wave function is actually invariant. I mean, these wave functions or the Hamiltonian will be periodic in theta from 0 to 2 pi. That's why I want to introduce theta, because I want to make the problem look simpler. Okay, so and then what you will have is this whole resistivity, whole conductivity. Then it will becomes, I think it will becomes as minus. Let me see. Let me actually. Let me introduce a few more things. One is that I want to introduce so-called Barry connection. That I write as curly AI. That is it's all called Barry connections. So it appears in the context of Barry phase, which I will explain in a minute. But so I just introduce this quantity, and then I can. So it's actually an analog of vector potential that we deal with in the in the electromagnetism, right? That's also the vector potential we play with in these lectures, right? And then we can introduce I think it's Barry curvature, right? That is, let me write it as fancy F. That's really, I mean, in the analog of the electromagnetism, that's really just my magnetic field, right? And with a little bit work, you would realize that this fxy is really just this term with some numerical factor. So then you will have, what we can have is that now this sigma xy will equals to it just equals to this guy. Okay, this is. Yeah, and let's do one further thing, that is that's average over theta x and theta y, since they are periodic. So let's just integrate over this theta x and theta y, and over fxy, right? That's the, so so we end up with this guy, this formula, and what we are going to show is that this will be quantized. And formally, the Chern number, the definition of the Chern number, so that's actually rewrite it a little bit. So we put 2 pi here, and leave only 1 2 pi here. Okay, so you will recognize that this piece is really just the one that we have for the Hall resistivity or conductivity right here, right? And the second piece, the things in the integral is called the Chern number that we will show it. It will be quantized. So let me write down. That's called Chern number. D theta x, integral over theta x and theta y over 2 pi and fx y, right? And this is called Chern number, and it will always quantized to be an integer. So that is, this is a mathematical theorem that I'm going to prove in a minute. But I hope you get the sense that why this whole conductivity in the end is always quantized values. So let me also point out that in condensed matter literature, this is called TKKN number. Although initially it was discussed in a slightly different setup. It was discussed on the lattice instead of a continuum that we consider here. But in the end, the essence is very similar. And that was really the work that opens this the entire industry of the topological materials or topological quantum matter that many people are working on nowadays. Okay, and the rest of this lecture is really want to prove that the statement that this Chern number is a quantized integer. Any questions? Yeah.
That's the Chern number, and what's the TKKA number?
Oh yeah, it's the same. It's at that time people are not condensed matter. People are not that familiar with topology, right? No one really thought about that. Then they kind of formulate this in their language, right? And in the end, it turns out that it's really just the Chern number that was discussed by mathematician Chern. Yeah, it turns out to be the same. Yeah. Yeah. Yeah, you can view A as some gauge field, right? So that's, yeah, it's this guy is gauge dependent, but this curvature is not, right? It's really just like the electromagnetism is actually just a special example of this, right? It's derived from using the Kubo formula, which I don't have time to explain. Yeah, you can check, let's say, Daviton's lecture notes about how to derive it. So the goal is for this lecture is really to explain that. Let's say we by admitting that using Kubo formula we can end up with this conductivity. This formula for conductivity, then the task for us to really prove that is a quantized number, right? No matter what this wave function looks like, no matter how messy it is, right? It's always an integer, right? Okay, so to prove this, we maybe let's also think this concept of Berry phase. Let me also introduce the concept of Berry phase. So I think you probably learned Berry phase in quantum mechanics course, do you? Okay, but yeah, but what I'm going to say is going to be pretty simple. Yeah, I will not assume you really learned Berry phase before. Okay, so it's actually just in a so I'm going to, Berry phase, the setup for the physics of Berry phase is very similar as here, right? Here, the essence is that I consider a perturbably Hamiltonian, or I consider a situation that I have my Hamiltonians depends on two parameters, right? Phi x and phi y, right? Then I can, with then varying this phi x and phi y, I end up with the wave functions, right, that depends on phi x and phi y, depends on those parameters, right? Then I can ask what the system will behave and so on, right? The Berry phase is very similar. It's the same. So in generally, what I can consider is that, let's say we just have a Hamiltonian depends on some parameters. That's like the phi x and phi y here. And it will depends on this lambda 1, lambda 2, and so on, right? And then now we consider a situation that I'm slowly varying those parameters. And then the point is I want to change those parameters very slow, such that the wave functions of the system will always stays in the ground state of that Hamiltonian. That is called a adiabatic theorem. I'm considering this situation, and then let's say then we consider an evolution such that my parameters lambda I forms a closed path in the parameter space, right? So that means after this evolution, my wave function goes back to itself, right? Right, because I'm ending up with the exactly same Hamiltonian, right? But there could be a phase factor, right, in front of it, right? We learned in quantum mechanics that, right, there's a phase degree of freedom, and this phase is called a Berry phase. And the way that you define Berry phase is exactly the way that you can compute Berry phase is really just use this, right? That's why I call it a Berry connection. So let's say we have this, let me write it again in the context of here. So I can define a Berry connection, which is, let me try to use the same notation. Right, that's really just the same thing, right? And it's very straightforward to compute, right? Let's say we have a wave function, depends on those parameters, then we just do a derivative with respect to some parameters, then we get this Berry curvature, Berry connection, right? And now we consider, so now we say, now let's say how this Berry connection is related to the phase factor. So let me write it. This is called Berry phase. How this Berry connection is related to the Berry phase, right? So we just consider a adiabatic time evolution such that I have my wave functions. The wave function will have some non-trivial phase factor coming from the evolution. And so schematically, I can have a wave function like this, right? So I'm really just slowly changing my Hamiltonian such that the state always stays in the ground state of that Hamiltonian, right? But the time evolution can give me a non-trivial phase factor, right? And this non-trivial phase factor can be just computed using the Schrodinger equation, right? It will just equals to my Hamiltonian times this state. Right? Yeah, that's really just Schrodinger equation. And then you can, let's say, you can expand the left-hand side, and for this, you will end up with let me say, you will end up with I h bar times I partial t phi t and my state. Let me omit those parameters, lambda I here, and e I phi t partial t right. That's what we have, right? And we can further change this to let me not write this term. Then we can further change this term to partial lambda I, and then we do a partial of lambda I with respect to t, right? That's what we can have. So now what we do is that we multiply the state with this equation with the conjugate of the state, right? Then we get a lot of those things canceled, and then we can end up with a formula that is, what should I do? Let me actually erase here. We end up with this thing. This factor will be I phi lambda partial lambda I that's what we will end up with. So you can try to repeat this computation, and then from this we will know the phase factor, right? You just do an integral with time, then you will get phi 0. It equals to integral. Now here it will becomes like integral for the first term, it will become the integral in the my parameter space lambda. It will be time independent. And the second term will be just a trivial term from the dynamic, from the energy, right? So, and now you say that the phase coming from this evolution is really just an integral of my Berry connection, right? That's why that's why Berry connection is very important in this in the story of Berry phase. And you can further show that, for example, this Berry connection, just like the vector potential, is gauge dependent, right? You can, let's say, you can redefine your wave function with some non-trivial phase factor that lambda dependent. And then you can easily say that this Berry connection is gauge dependent, but the Berry phase for the situation that you consider a closed loop, right? Let me write a closed loop. Let's say if you consider a closed loop, then you do get this. The Berry phase will be gauge independent, right? That's the Berry phase. Yeah, the energy of a ground state. Yeah, yeah.
Also in the Berry connection, there is a dependent of I. What is in the formula?
Okay. So for this I, that's the imaginary I. So yeah. This I is the. So it's really like the path you have, right? This lambda I, let's say you consider multiple parameter space, right? And then this lambda I will be just be the. Let me actually draw a picture for that. So just back to the Chern number case that we consider. So we consider. So remember in our Chern number case, we have theta x, theta y, right? That's my parameter space, right? Then those theta x and theta y is periodic, right? So what we can have is really a torus, right, for the theta and y space, right? They're periodic. Now, what the Berry phase is really that you just consider any loop in the system, right? Consider some evolution around a closed loop in my parameter space. And then we can ask, as my system goes through this closed loop in my parameter space, what's the phase factor that we get? And that is a Berry phase factor. And then the way to compute it is really that the way that you compute it, this gamma is my Berry phase, will be exponential minus I. I may mess up some sign here, so sorry for the being sloppy. So let's say we call this loop as C, and then the Berry phase is really just compute this, right? And this AI is the connection, Berry connection that I have in my parameter space, and then I just compute it as this. Okay. Because I start with my setup is that I have a Hamiltonian, which the Hamiltonian depends on those parameters, right? Yeah. For example, like in this case, what I have is I consider this. I put my two-dimensional electron gas in the torus, right? Then I insert flux, this phi x and phi y, right? Then I slowly change those phi x and phi y, right? That's the situation, yeah, right? So that's the bare face. And remember that here we also introduced the Berry curvature, right? And so indeed, just use Stokes theorem, right? You can rewrite this integral as let me, how should I call it? Let me call it small a. It just means the area of this closed by the loop, right? I can rewrite this. Just use Stokes theorem. I can rewrite this integral as an integral in the area closed by the loop, right? Because f is just defined as dA, right? So so f, this curvature is really just this, right? Then I can use Stokes theorem, right? So this is very close to the Chern number formulations that formula that we have here, right? So now, but for Chern number, what we have is that for this Chern number, what we have is that the integral of the entire torus, right? But now the Berry face for Berry face is an integral for the region that closed by the loop. Now comes the proof for the Chern number to be an integer, right? So so here we relate the Berry face coming from this closed loop with the integral of an area closed by the loop, right? But I can also view this integral alternatively, right? Because I have a closed surface for this loop, right? I can also say this loop encloses the rest of the entire system, right? That's the same, right? And you can then do this. I think that there should be a minus sign there. Depends on how do you do the integral for the directions, right? And that should be equal to each other, right? Right. And now we just prove that so I think yeah, there should be a 2 pi somewhere. Let me see. Yeah. Yeah. I think there should be 2 pi somewhere. So yeah. Yeah, let me see. Oh no. That's for yeah, just like this. Yeah. So then what do you so it must be the case that those two different ways of doing the integral should give me the identical answer, right? And then that is really just mean that yeah,
Excuse me, could I make some question?
yeah, sure.
All right, if I'm getting it right, then the Chern number is just an integer that comes merely from the fact of studying the topology of a toroidal surface, which has some flux going through it, which is specifically real, continuous, and most importantly, finite, right?
Yeah.
All right, so let's include, and I'm not really sure what this a sub I means. I'm not sure if I'm mentioning something, but what are these things?
You don't, not sure about what means.
It's better if you repeat the question.
I mean, I'm not sure what this a sub I means. What
AI.
does it refer to? Yes.
Yeah. The question is, what does this? You mean what does I means or AI?
Yeah, I mean that's an array, right?
No. That's the Berry connection. That's the Berry connection defines in this way, right?
All right, and so how could we understand this magnitude?
understand it what?
I'm not sure what that is. Basically.
So remember, I have a Hamiltonian that depends on those two parameters, right? Phi x and phi y, right? And then the wave function, the ground state, the wave function of that, the ground state of that Hamiltonian will just be this wave function, depends on phi x and phi y, and then I can then, using this wave function, I can define this Berry connection, right? That's a game. And then I can also define this so-called Berry curvature, which is looks like this. And then the claim is then using Kubo formula, you can rewrite the Chern number or Hall conductivity as the integral of the Berry curvature.
And does the Berry connection have a physical
The Berry connection
meaning?
does, well, it's gauge dependent, right? So in gauge theory or electromagnetism that we play with, the vector potential is one type of Berry connection. And then the Berry curvature is really just the magnetic field in the electromagnetism. Okay, that's that clear? Yeah.
Can you repeat how do we go from this notion over here that it is from a lot of particles,
Yeah.
this one that depends on two variables?
So okay, this function also, I mean, this wave function also is a function of those coordinates. I'm just not writing them explicitly. Yeah, yeah. It's just like for each pair of phi x and phi y, we will have a wave function. Many body wave function looks like this form, right? But its precise form is not important for our discussion. So we end up with this. So then we know this integral should be 2 pi times an integer, right? That's how we prove Chern number is an integer. Yeah, here I may use a slide. Yeah, I think I'm right. Yeah, so that's how we can prove the Chern number is an integer. Chern number is defined by the integral over 2 pi, right? That's how we define the integer, right? So then we derive that the y Chern number is an integer. As you can see, it's really pretty simple that you just consider the Berry phase that on a closed manifold like a torus. Then the fact that is for that Berry phase, we do have two ways to compute it using Berry curvature, right? And then those two ways of computation should give me the identical answer, right? And that then shows the why it is an integer, right? And as I have already explained, the electromagnetism is one simple example of those like connection and the curvatures, right? And we learned in quantum mechanics. Just reminds you, I just try to connect this discussion with something you might be more familiar with, right? It's this Aharonov-Bohm phase, right? We talk about. We also mentioned in the past, right? Right, the Aharonov-Bohm phase is a special example of Berry phase Berry curvature, right? There, I think you should have learned this in quantum mechanics, right? So there, so just let's say we have some magnetic flux in the system, right? Phi, and then I have some particles, right? Encircle that magnetic flux, right? So then you know there will be a non-trivial phase factor, this Aharonov bone phase, right? Gamma is really just comes from the magnetic flux, right? Times some physical constant, right? And this is really just a Berry phase, right? And here you know that the Berry phase, the value of Berry phase comes from the magnetic flux, right? The magnetic flux is B times area, and that's really just the integral of your Berry curvature, right? The magnetic field is one type of, a special type of Berry curvature, right? And in the Aharonov bone phase effect, you also know that you can equivalently compute this phase factor just using this type of formula, right? You just do the integral of your chemical potential, vector potential along the circle, right? Then you get this Aharonov bone phase, right? So yeah, I think I'm running out of time. So I hope that it's now you get the idea that why this whole conductivity is a quantized value, right? So let me try to conclude, right? So in this mini course, I talk about this. I introduced the experimental phenomenon of those quantum Hall effect, right? I talked about integer quantum Hall effect, and I also tell you about fractional quantum Hall effect, although I don't have time to explain what's the physical mechanism of fractional quantum Hall effect. And for integer quantum Hall effect, there are two key factors to make it happen. The first key factor is that it's pretty counterintuitive. That is, in the real world, we have impurity, we have disorders, and it is those dirtiness of the real sample really makes this robust, extraordinarily precise quantized plateaus of my Hall resistivity, right? And then the reason that those Hall resistivity or conductivity gets quantized rather than some other random numbers comes from the fact that you can relate them with the Chern number, and then the Chern number is a topological invariant which has to be an integer. That's why in the end you end up with that's how we can understand this integer, the quantized Hall resistivity observed experimentally. All right, so I think I can still take a few questions.
Yes, now we are in discussion session.
Yeah. Yeah, it's a Berry connection related to the connection in the differential geometry and so on, right? The answer is yes. Yeah.
Do you know about quaternion phase?
Sorry?
Do you know about quaternion phase?
What phase? I missed the word before the phase.
It's a huge name from one Indian that first discovered the Berry phase and then Berry formulated
Okay.
more precise.
Okay. Yeah. At some point, I know that. I knew that, but I forgot. Yeah.
Yeah, I wonder how is the connection with
But it's the same. Yeah.
Professor, you have done all that algebra on using the angles on the toroid, but what's exactly the relation between the toroid and this problem?
Okay. So the which toroid you are talking about actually? I have two toroids, right? One is like just the physical toroid that I have for my physical system. The other toroid is the torus in the in the parameter space of this flux. So which are you asking about? Oh,
Okay.
okay, sorry.
Uh, it's just that this effect, the quantum round effect, it's found on it. At least by what I understood, it's not dependent on the shape of my circuit. So
Yeah,
why
okay.
use the toroid specific?
Okay, yeah. That's a good question. So the torus is here is, yeah. In the end, the answer should be independent of shape and the geometry or topology of the system. You are right, but by making use of this torus geometry, we can. It's more convenient for us to reach the conclusion that the conductivity is quantized. Right.
Is this periodic boundary?
Yeah, it's a periodic boundary condition. Right.
Thank you very much.
Yeah. So it's pretty often in physics that you choose some special geometry or topology such that you can make the physical argument more convenient. Right?
Yeah, please go ahead. Are you climbing up? I can.
So I'm trying to understand a little bit better of the microscopic point of view of this. So is as I the electrons when they generate this phase from integer numbers for each time they go around the torus, or I didn't understand a little bit how the microscopic point of view is related to the integer of the resistivity.
Yeah. So the idea is that here we consider this setup, right? I have my Hamiltonian defined on a torus, right? And then I can add two flux, right, in two different directions in the torus, right? I get a new Hamiltonian, right? Depends on phi x and phi y, right? And then for this, using this setup, then I can make use of this so-called Kubo formula to rewrite my conductivity as this formula. Right? That's the idea.
But I mean, this is an integer number, right? And I'm trying to understand why this flux makes this become an integer number than just any other number, just like in the classical Hall effect. I mean, where disorder entered here is
Why what
in this
enters
part
here?
for
Disorder doesn't enter in this part. But the discussion here applies to any situation, including the clean case, as well as disorder case, or you can add interactions to it. Right. It's a pretty formal setup that I just have some Hamiltonian defined on torus, then I add flux in two directions, I get some flux-dependent Hamiltonians, and then just using this, I can compute the conductivity using a Kubo formula, and it turns out to be this. Right?
Questions there in the front?
Yeah, so, excuse me. Then what you just said is that in this framework, we can describe the quantization because of the topology, but we still need disorder to completely talk about the curves, the straight lines that we see on the experiment, right?
Yeah.
Right, and one more question. If I find myself in an experimental environment, all of the computations that I might need to do were the ones that we already saw last class. Am I right?
Could you repeat the question?
Yes, that if I find myself in an experimental environment and I'd like to get a glimpse of this effect in my measurements, all of the computations for me to prepare the experiment were the ones that I might need to do, were the ones that we already saw last class. Is that right?
Not quite right. The thing is, you don't know what those like disorder potential look like in your real sample, right? It's just going to be a mass, right? Yeah. The beauty of those related to the topology is that you don't need to care about the mass. In the end, it will just be a quantized number, right? And also, in reality, you also have interactions, right, which we don't have chance to talk about. And then the point is the interactions also will not change the story.
All right, but if I, let's say, compute the magnetic length, I already have like a way to start or something like that, right?
I don't know what you can get from there.
Let's say that I want to measure this line in an experiment. What computations should I do beforehand to?
If you want to measure it, then you just measure it, right? You don't need to do any computation, right? You just like how people measure the Hall resistivity, then you measure it, right? Right.
All right.
The phi x and phi y are just two examples, or in our case, are just two examples of these parameters, lambda.
Right.
Okay. Should it be better if we have this definition of Berry connection and Berry curvature with a lambda? With a lambda?
Yeah, they're just.
For our case, and also, you mentioned that you choose these phi x and phi y because they have periodic boundary conditions, no? Because it's also, but we can also choose this lambda, these parameters, just from these periodical conditions, or can we also choose it from knowing that physical, like having a definition of physical, a physical definition of these parameters maybe can help also, or not?
Yeah,
or
you can put it on any geometry you like.
But they
such
have
as torus, a sphere,
okay.
or anything you like.
And we can always, in any geometry, we can always have this number, this integer number.
Yeah. You say that the argument here doesn't really rely on I have a
the
torus or some other geometry like sphere, right?
Okay.
So what you really need is a closed surface, closed space, right? Such that I can have this. Right?
Okay. In this case, phi x and phi y, does it have any relation with the chi x, with kx and ky with the momentum?
Yeah, it has some relations. Yeah. So indeed, this TKN was originally formulated using on a lattice with the momentums and so on. That's the way they formulated it.
Okay, thank you.
Maybe you can do a comment about can I do a comment? No problem.
Yeah.
Well, I understand that the Berry connection and the Berry curvature are something that happened because the general geometry, the differential geometry. The Chern number, I understand, is like, for example, the counting the holes that is in the manifold, something like that. Because I see it's related, maybe because I understand, for example, in the geometry of, in the topology of the space-time, you have something similar, no? That you count. I understand the theorem of Gauss theorem.
The Euler characteristic counts the whole, right? It's a different topology invariant from Chern number.
Okay.
At least at quantum field theory, we usually find a connection after we impose that the covariant derivative, it transforms the same way as the field, right? So what would be the local phase transformation would have here, and what would be the form of the covariant derivative?
Yeah, so you can view this Berry connection as a vector potential, right? Then you can use it to define a covariant.
But we have a local phase transformation for some kind of field.
Yeah,
there.
that's correspond to, let's say, you can rotate the phase factor of your wave function locally, right?
And the covariant derivative would be wouldn't be a partial derivative of the space-time. Would be
Then it's a
derivative
partial
over
derivative
theta.
in the parameter space.
All right. All right. Thank you.
Okay, if there are no more questions, let's thank Yin-Che again for a very nice course.
Thank you.